Section 2.2, histograms, aka bar graphs. Again, very important stuff. This is really one of the most foundational sections in the course. So here are the main topics for today: converting a frequency distribution to a histogram and vice versa. 1- and 2-dimensional measurements. This is really not explicitly addressed in the book or in most courses, but I find it to be very conceptually important. Outliers, which I don't find to be as important, but it is kind of the textbook and your quizzes kind of seem to have a fascination with outliers. So we better address those for the purposes of this class. And then basic shapes. When we draw a histogram, we're going to see that there are different shapes that I can assume. So a histogram or a bar graph is it's a visual. It's a two-dimensional visualization of data or a frequency distribution. And in order to illustrate it, I think it's just best to show you one. And the example that I'm going to use is the same example we used in section 2.1 about the number of children in various families. Over here, I've actually reproduced the whole ordered list. So this format is what StatCrunch would call data, whereas the table over here is a summary of the data, and that'll be important in just a second when we make our choice. Let's go ahead and work with the frequency distribution first. We go to graph and bar plot. Make sure that you choose bar plot here and not histogram. Bar plot, and remember what I said just a second ago, that a frequency distribution is a summary of a long list of numbers. So that's why I'm going to click with summary here. And now it's going to ask us for some guidance. Your categories are well, in this example, the categories were the number of children. 0 children is a category. 1 child is another category. So those categories here are listed in the children column. The counts or the frequencies are listed in the families column. I don't think we have to click anything else here. I'm gonna just click compute. There we go. Okay, so what we see here is a two-dimensional graph. We see horizontal and vertical, where the horizontal axis here is the children, the categories, the number of children is what we call the random variable in the last section. And then the frequency with which those values of the variable occur are plotted on the vertical. So that gives us 6 different rectangles, each corresponding to a class in this table. So for example, if we look at the category of 0 children, it has a frequency of 3, and that frequency is drawn as the height of this bar or rectangle. 1 child has a frequency of 5. So that's repeated for all 6 of the categories. So I hope you can see that this is basically representing the exact same information that we see over here, but in this case, we've basically turned each one of these into a dimension so we can see it two-dimensionally. And that's really nice for human consumption because we like to be able to look at things like this. And for example, it can tell us things about shapes that really are not so evident when we just look at numbers like that. By the way, if we want to construct one of these from raw data, it's pretty similar. We go graph, bar plot with data, and indicate that we're looking at the list this time. And I don't think we have to click anything else again. The process is going to be slightly different when we have grouped data. But in this case, I've just drawn a separate rectangle for each individual value in the list. So it should look the same because it's the same information. All right, so that's basically what a frequency distribution, what a histogram is and how we can convert a frequency distribution into a histogram. Remember that being able to do that in reverse is also super important. And before we do that, I want to emphasize these issues about horizontal and vertical and 1 and 2 dimensions. So when we look at that kind of a graph, the x, in this case number of children, is graphed horizontally, And that means that it goes from small to large as we go from left to right. So let's just look at that together. Again, if I pull one of those up, children, families. Okay. So the number of children, as we go from left to right, we're actually going from small to large in the number of children. And then on the vertical axis, as we go from bottom to top, we are going from less common to more common, right? This rectangle is short. Doesn't mean that it's a small number. It means that it's an uncommon number. It only has a frequency of 1. This bar is tall. That doesn't mean that it's a big number. 2 is not a large number of children, but it's tall because it's such a common value in this list, okay? So again, horizontally left to right, we go from small to large values of our variable, and as we go up, we are going from less common to more common. You can also see that, as I indicated before, when we put these two variables together, we really have to think about it as an integrated two-dimensional shape. And each one of these rectangles has not only a height, but also an area. And you can think about each rectangle's height as representing its probability. I think that if I remember correctly, there are 25 families in this whole list, so we could just as well write this as a probability and say that this bar is 3/25 probability. We could also say that the probability corresponds to the area of this rectangle. Now, you might wonder why we would want to do that. Why would we want to measure the area of a rectangle when its height is so much easier to see? But that is going to be a very important issue when we make the progression from what's called discrete distributions to continuous distributions, which are going to form the bulk of this class, actually. So I want to kind of get you, I basically just want to foreshadow this issue right now, that when we look at a two-dimensional graph, we are going to be thinking about area as representing probability. Now, let's go back to this. Actually, let me go to this examples page now. All right. So here is a new example. I've drawn a histogram with horizontal and vertical axes and some rectangles. And in order to make this problem a little bit not too obvious, I've numbered these things. I've lettered these values instead of numbering them. So here's a histogram with rectangles sitting on values A, B, C, and D. And I'm going to give you some multiple choice questions now. What would you say is the smallest number in this data set? What's the smallest number in this data set? Well, remember that when we think about going from small to large, that's really associated with going from left to right. So a lot of students would say the smallest number, let me see. Oh, that must be C because the C rectangle is so short. No. Small means to the left. So the smallest number in this data set is number A. Now, what's the least common number in this data set? Okay, when we think about common, we're thinking about frequency, we're thinking vertically. Okay, so the least common value would be the one with the shortest rectangle. That would be rectangle C. Now, I hope these other questions are going to be easier for you now. What is the largest number in this data set? Is it A, B, C, or D? I hope you said D because that number is farthest to the right. And finally, what's the most common number in this data set? Well, I hope you said B because it is associated with the tallest rectangle. All right, I also want to take a look at shapes. Oh, yeah, let's go ahead and hit shapes, and then we'll come back to outliers. So when we have a graph in front of us, we have a nice two-dimensional shape to look at. It's a great visual aid. And we can learn a lot at a glance just by taking a look at basically what kind of shape it has. So here are some of the most common shapes. it's very common to end up with symmetric shapes that peak in the middle. This is also called bell-shaped, and a special example of a bell-shaped curve is called the normal curve. Now, technically, normal is a very technical, narrow meaning, but for the purposes of your homework in this chapter, you can basically regard normal and bell-shaped as being synonymous. In truth, normal is just one special example of a bell curve. Some distributions are uniform, which basically means that every value is equally likely. Remember, since this graph doesn't have any bars that are shorter or taller than others, they are all equally tall, meaning equally likely. And you would get something like that, for example, if you kept track of how many people were born in each month of the year. You would expect there to be about as many births in February as May, or any number of months, really. Any pair of months. Okay, now some graphs peak, but not in the center. So here's an example of a graph that peaks farther, it's kind of to the right of center, and then it has a tail to the left of center. And here's the opposite. It's important to remember that we call this kind of a graph skewed, and that the skew follows the direction of the tail, not the peak. So that takes a little while to get used to. Some people want to call this graph skewed to the right because the peak is on the right, but it's the tail that skews it. So this has a long skinny tail to the left. This has a long skinny tail to the right. Skewed left, skew right. And then of course some graphs actually have two peaks. And you might find something like this if there were two distinct populations. The best example that I can think of would be if this graph represented the heights of adults. Why do you suppose it might have two peaks like that? The heights of adults. Well, maybe this peak represents the most common female heights, and this peak represents the most common male heights. And then, of course, some graphs are none of the above, just very irregular. But these are the most common and important ones. And finally, that brings us around to the topic of outliers. Outliers are numbers that are both rare and much smaller or larger than the others in the table. And these are really easy to see on a graph. So let's go back to our number of children example. And this time I want to introduce to you the Helton family. These are actually my great-great-grandparents, John and Mary Helton. And this is actually their family, photographed about a century ago. And this is my great-grandmother up here. I knew her. And if you can count them that quickly, they had 13 children who lived to adulthood. That doesn't even count the 3 who died in infancy. But let's just say that they have 13 surviving children. And let's add them to our list. They are definitely going to qualify as an outlier. So let's go back here and add the number 13 to our list. The number 13 appeared once. Or in this data set, we could just go ahead and put, we can just put a 13 down here. I'm having trouble scrolling. Okay, anyway. So let's make a graph now, a bar plot with the summary, children and families. And, well, this doesn't draw it to scale very well. I tell you what, I'm going to add empty spaces for the other rows. Okay, so now I've basically filled in the 6s and 7s with 0s, and I need to hurry up because I only have seconds left. But if we do our bar plot with summary now, children and families, and compute, now we get this graph. So this is the graph that we saw before, and now there's a long blank space, and there's a single 13 out here. It's short and far away from the rest of the data. So that's called an outlier. Outliers are kind of important because this is just one point in the list, but it can have kind of an impact on the statistics when we do them later on. All right, so we're going to have to leave it at that. I'll see you in the next clip.